Hi, welcome back. Today we're going to continue our discussion of singular value decomposition. We're going to talk about low rank approximation in a little bit, but first I want to continue talking about the geometry because we didn't quite finish last time. Right, last time we discussed this theorem, but so far all we've talked about is if you have an orthonormal matrix, then it sends, it preserves dot products, meaning it preserves angles and lengths, which means that if you take the sphere and you apply an orthonormal matrix, it just goes to the sphere again. So it fixes the sphere. Because what it will do is it will basically, it'll rotate the sphere. Plus maybe if it has determinant -1, it also might change the orientation in some way. But morally, it's like a rotation. Right? So it just takes this, so it takes the sphere to itself in some very nice way. But now I want to talk about this theorem, the theorem that we're trying to understand, which tells you how to understand what the linear transformation A is doing by using the singular value decomposition, right? Because the singular value decomposition says that you can understand A in three parts. First, it does V transpose, which is an orthonormal matrix. Then it does sigma, which is a very nice sparse matrix. Then it does U, which is another orthonormal matrix, right? So A is a matrix in Rm by n, meaning that A is a linear transformation from Rn to Rm. And we're going to write the singular value decomposition, A equals U sigma V transpose. And again, what V transpose does is V transpose changes basis to the columns of V. Right? This is a basis of Rn. Right? So what does that mean? It means that if you have V1, when you change basis, it looks like E1. It looks like 1, 0, 0, 0, 0, because in the basis V1 through Vn, it is the first basis vector. Right? It sends V2 to E2. So it's like we start in Rn, and this is the picture from the notes. I think it's a really good one. Let's just picture it as R2 for a second. And we have two vectors. I mean, we have an orthonormal basis of Rn. So in this case, I'll draw it as two vectors that look like this. And so I can think about the circle that they define. They define the unit circle or the unit sphere in Rn. And what V transpose does is it sends V1 to E1, and it sends V2 to E2. Again, because in the basis V1, V2, those are the basis vectors, so you would write them as 1, 0, and 0, 1. And as we just said in the last result, it sends the sphere to itself. Okay, now sigma does something really predictable. Sigma looks like this. So I guess in our case, okay, well, I want to try to be somewhat general here. Sigma looks like this, right? Which means that it sends the first basis vector to sigma 1 times the first basis vector, it sends the second basis vector to sigma 2 times the first basis vector, etc., and then it will send the rest to 0. Right? So you apply sigma to this thing, and what it does is it will send E1 to sigma 1 E1, and it will send E2 to sigma 2 E2. It could also send E2 to 0. That's also possible, right? Depending on what R is. So let's just draw it like this. Right? And because these sigmas are in decreasing order, we know that as you go E1, E2, E3, E4, they'll shrink, right? And note that, let me use a different notation because these are different basis vectors. This side is in Rn, but this side is in Rm. Right? So it's clear, okay, well, it's somewhat clear that then what you're doing is you're sending that sphere to this hyperellipse, right? Or maybe in another world, if like sigma 2 were 0, right? If it were a rank 1 matrix, then you would just be sending sigma 1, sorry, you'd just be sending E1 to sigma 1 E1, and you'd be sending E2 to 0, and so you would get like this degenerate ellipse, right? We said like this, the sphere is 2 points. So this is 2 possibilities. So this one has rank 2. This one has rank 1. Okay, and then what does U do? U changes basis from the standard basis, sorry, from U to the standard basis, right? Which means that we get the opposite picture here. This is written in the basis U. In the basis U, what is E1? That's U1. In the basis U, what is E2? Well, prime, that's U2. So there is some basis over here, U1 and U2. So maybe let's draw like U1 here and U2 here. Remember, it's again an orthonormal basis. And sigma 1 U1 is like this. Sigma 2 U2, I guess it looked a little bit smaller, so maybe this is sigma 2 U2. So you're setting it to this ellipse, right? Or in the rank 1 case, you'd be sending it to this degenerate ellipse, right? This is sigma 1 U1. So what we're saying is any matrix, we can find this choice of basis, this choice of orthonormal basis, where it's very easy to understand what A does. It's sending the sphere that's determined by, and you're choosing the basis V1, so that's you have a nice frame for your sphere, and it's sending it to a certain hyperellipse in Rm, an R-dimensional hyperellipse in Rm, and the U's are going to be the semi-axes of that ellipse. So you're identifying, the whole point of a singular value decomposition, one of the whole points, is you're identifying the basis, this basis here, which will go to these vectors here that give you the semi-axes of the ellipse. And the whole process is a change of basis followed by a nice linear transformation sigma that you can understand, followed by a change of basis. Okay? And let me just point out that in a way that we'll see in lots of applications, somehow the largest singular values are most of what the linear transformation is doing, in a way that will become precise as we look at applications. Okay. Right. So that, like, I gave you a rank 2 and a rank 1 example here in kind of a not great way. But the picture in the notes, which I think is actually maybe a bit better, is actually, if we look at R3, and A, there's several possibilities for A, right? A could have rank 3, it could have rank 2, it could have rank 1. It could also have rank 0, I guess, but then it would just be the 0 matrix, right? And again, the rank is at most the dimension of the domain and the dimension of the codomain, whichever one is smaller, because that's the number of rows or the number of columns, right? And again, we've identified some orthonormal basis, right? So maybe this is V1, this is V2, this is V3. So imagine these are all length 1 vectors that are mutually orthogonal, right? So there are right angles everywhere here. This is a right angle. It will send it to some hyperellipse where the axes I mean, the semi-axes will be given by another orthonormal frame. Those will be the u's. But the rank tells you what dimension the hyperellipse is. So if it's a rank 3 one, then you are sending it in Rm to some three-dimensional hyperellipse. Right, there's 3 axes, and the longest one will be, this is sigma 1 u1, and the second longest one is sigma 2 u2, and the third longest one, which I guess is coming out this way, is sigma 3 u3. That's if you have a rank 3 matrix. If it's rank 2, it sends this sphere to a 2-dimensional hyperellipse, which is just an ellipse, right? An ellipse that you would recognize from. Let's try to draw it somewhat nicely. And there's only 2 axes that matter here, right? So this is sigma 1 u1, and this one is sigma 2 u2. And of course, if it's rank 1, then it really just sends it to the degenerate ellipse, which is just 2 points. And this is sigma 1 u1. Okay, so the SVD tells you how you send a sphere to a hyperellipse from the domain to the codomain, depending on the rank of A, and then the axes directions are determined by the left and the right singular vectors, and the scaling factor is determined by the singular values. That's all the pieces of the singular value decomposition. Okay, and that's an explanation of every part of this theorem here. Right, so the sphere maps to an r-dimensional hyperellipse in Rm. The lengths of the semi-axes are these singular values because of, because of this picture here. Right, the point is this bottom linear transformation, you're setting the standard basis, and all you're doing is you're just scaling in various directions, which will determine an ellipse. And so you're giving the various semi-axes of the ellipse, and the amount you scale, that ends up being the length of the semi-axis, right? Back to here. The first R left singular vectors are the unit vectors along the semi-axes. That's what we were seeing in somewhat in this picture, right? The point is that only the first R things are not going to 0. So the first R things are determining the hyperellipse that you get sent to. Okay, and then the first R right singular vectors are the pre-images of the semi-axes. Well, that's encapsulated in all these pictures, I guess. Right, the point is that what is the pre-image of this highlighted vector? The pre-image of this highlighted vector under A, right? Altogether, this whole thing gives you A. It's this vector here. So the left singular vectors tell you which things map over to the semi-axes of the hyperellipse that you get when you map this sphere over. Okay, so if you can understand these pictures, it tells you, I mean, it will be a lot easier to understand what's happening in the applications and the examples, because basically all of the data of the singular value decomposition is telling you really important things about how the matrix is actually acting. Okay, but the application I want to get to today is low rank matrix approximation. Okay, and you can think of this kind of like, in some sense you can think of it kind of like trying to approximate a function with like a polynomial. So we know that like if you take, let me just give you the analogy. If you take any function, let's say infinitely differentiable function, f, like for example e to the x or sine x or whatever you want, that's infinitely differentiable, you know that you can write down the Taylor series, right? From this, you can get the Taylor series, which is an infinite series of some coefficients and some powers of x, right? Of course, this is like the nth derivative divided by n factorial, right? And I guess it depends on where you expand it. So this is really a Maclaurin series, but regardless, you know you can do this, and then you could truncate it, right? So then you could get Taylor polynomials, which is just the first however many terms of your Taylor series. And the point is that this Taylor polynomial, this approximates the function with a really simple thing, right? So the top function might be something that you have no idea how to integrate, how to differentiate, how to graph. But a polynomial is a very nice thing that you know how to differentiate, integrate, graph. So there's oftentimes you want to approximate some complicated object with some simpler objects, right? And low rank matrices are simpler than high rank matrices, because low rank matrices have like smaller column spaces, right? There's fewer linearly independent columns or fewer linearly independent rows. So what we'd like to do is we'd like to approximate a matrix A with a lower rank matrix. Let's say A prime. Let's just call it A prime for now. Okay, but once you say, I want to approximate something, you want to know how good is your approximation, which means that you need to know how far away is the approximation from the thing that you want to approximate. Right? Otherwise, if you have no notion of how good an approximation is, then if I give you any polynomial, right, if this is the function e to the x, there's going to be a best degree 3 polynomial that approximates e to the x. You need to know how close is a polynomial to e to the x. You need some measure. And there's many different ways to measure how close a function is to another function. Okay, there's infinitely many different ways. But if I want to know how well a matrix is approximated by another matrix, I need some notion of how far away two matrices are from one another. Right, so to know if I have a good approximation, or whether or not I have a good approximation, I need to know how far apart are A and A prime. And then if I pick a rank, I should be able to find the closest matrix to A that has rank k. Just like if I pick a degree 3, I should be able to find a closest polynomial that approximates e to the x. And usually this is done by, you take the integral of the difference along some interval, say. And so if you center your interval at wherever you're expanding your Taylor series, you can prove that the Taylor series is the best approximation. Is that true by that norm? I actually don't know if that's true or not. But it doesn't matter for this course anyway. Okay, so how far apart are two matrices? What I want is I want a notion of distance between matrices, which we sometimes call a norm. And that's what I'm going to introduce right now. It's a very important norm. It's a very important notion of distance. Okay, so of course, for vectors, in Rn, we have a notion of distance. Right, because we defined this, if x is x1 through xn, we defined this norm of x to be the square root of the sums of the squares of the components. Okay, this is called, if you're an analyst, you might call this the 2 norm. So this is the 2 norm. And you call it the 2 norm because you're taking squares and square roots. You could also take, say, the cube root of the sum of the cubes. That would be the 3 norm. Okay, so because this is called the 2 norm, I'm gonna sometimes decorate this with a 2 underneath. Okay. Now what I'm gonna do is going to define a norm on matrices, something that tells me how big a matrix is in some sense. And then I can tell how close two matrices are, because if I take their difference, I can take the norm of the difference. That would tell me how far away the two matrices are. So here's the definition. So let A be some matrix Aij. Actually, I don't think I actually need. I don't need the entries of A. So this is a matrix in R m by n. Then the 2 norm of A. So I'm defining it now for matrices. This is the 2 norm for vectors. This 2 norm is for matrices. So the 2 norm of A, or the spectral norm, of A is the following thing. So I'm going to denote it the same way. So 2 norm, it's a norm depending on the number 2. And it's going to be the max over all non-zero vectors x of the following quantity, the 2 norm of ax divided by the 2 norm of x. Okay, the point is that these things, let me use some colors here. These things are vectors. So I really just mean the Euclidean norm. So what am I doing? I'm taking every vector in Rn, and I'm multiplying it by A, and I'm seeing how did A change the length of X. And I want to see the maximum stretch that A did in any direction, and that's what I'm going to call the norm of A. The norm of A is the maximum distance it ever stretches any vector. Right? That's the in quotes, the max stretch factor over all vectors. Okay, this is in principle something that you need to check on every possible vector, right? But one thing that we know is that if alpha is a real number, then the norm of alpha x is equal to the alpha times the norm of x. Right? In other words, if A scales x by 2, it also scales 10x by 2. Right? Because you can just pull it out of the norm, and then you get the same factor on the numerator and the denominator. So even though this definition says you need to test over all vectors x, you can check just every unit vector. So you can look at just the sphere, and you can see what's the furthest direction that A stretches any part of the sphere. That will be the 2 norm, or the spectral norm of A. Right? So because this is true, if I looked at this is equal to alpha times ax over alpha times x, which is just ax over x, which means that we don't need to worry about different scalings. We might as well take all the vectors to be unit vectors. So this thing is in fact equal to the max over all x that is actually has norm 1, just the sphere of this quantity. I'm going to erase it in 1 second, because the norm, the denominator is just 1, so it's just the max of this over all vectors of length 1. So it's the max stretch factor over all unit vectors. That's what the 2 norm is. Okay, but the point is that now that we've studied the singular value decomposition, we know exactly what the 2 norm of any matrix is. Because of this picture, or this picture. Here I've drawn in every vector of every unit vector. That's the sphere. What's the maximum any of them stretch to? Well, it's just the longest semi-axis of the ellipse. What is that length? That length is just the first singular value. Okay, so by our results on SVD, the 2 norm of A is equal to the largest singular value of A. Okay, recall also that the singular value decomposition gave us a way to write any matrix as a sum of rank 1 matrices. It's also recall that A is equal to the sum from I equals 1 to R of sigma I ui vi transpose. Right, and each of these was rank 1. Because at the last step, you're multiplying by a column vector, which means that the range was at most one-dimensional, and it was a non-zero column vector, so it was actually one-dimensional. Right? I mean, also here I have a sum of R matrices. Each of them has rank at most 1, but we know that A has rank R. So in other words, at every stage, I must be adding the rank of one rank. I must be incrementing the rank by 1 at each step, right? So this is, if I just write it out like this, let me just write out a few terms. Right, the point is that we know that the sum has rank R. A has rank R. This one has rank 1. But at each stage, the most the rank could be going up is 1. Because I'm adding a rank 1 matrix. It's possible to add 2 rank 1 matrices and stay rank 1. Right? If I added this matrix to this matrix, these are both rank 1 matrices, but their sum is also rank 1. But in the end, I'm getting a rank R matrix, which means that at each step, this thing must have rank 2, and this thing must have rank 3. So the SVD is actually giving us a way to approximate a matrix for any rank between 1 and R, which is the rank of the matrix. Of course, if you want to approximate A with a rank R matrix, the best you can do is A. A itself is rank R. It's like saying if I want to approximate a degree 5 polynomial by a degree 5 polynomial, I just give you the polynomial itself. And so really the SVD gives us a rank K matrix for any K between 1 and R, and this matrix is somehow related to A, right? It's built out of, okay, there's other ways to do it. I could also start from the back. I could take any combination of them, but I've chosen them from the front for a reason. The reason I've chosen them from the front is because it turns out that these will actually end up being the best rank K approximation for A. The best in what sense? The best in the sense if you take the difference to A, you minimize the 2 norm of the difference. It's the closest in the 2 norm to A for each rank. Okay, so let me call this a definition. Let rank of A be R, as always. For any K between 1 and R. Okay, let's say between 1 and R and not include R because you're not approximating if you're at R. You have the exact answer. The rank K approximation, the rank K approximation to A is the kth partial sum a sigma 1 u1 v1 transpose plus sigma k uk vk transpose sigma I ui vi transpose. Okay, so you take the k largest singular values and the corresponding left and right singular vectors, and you build this matrix. This thing is a rank k. Let's call it, oh, sorry, this is called AK. And the rank of AK is just k. Okay, and it's a theorem that this is the best approximation in the sense that it minimizes the 2 norm amongst all possible rank k matrices. And this theorem is famous. It has a name. It's called the Eckart-Young theorem. Okay, so this is due to Eckart and Young. So the closest, okay, let me say, for all k between 1 and r, the closest rank k matrix to A in 2 norm is AK. That is, if B is any rank k matrix, then the difference between A and B in 2 norm is at least as big as the difference between A and AK in 2 norm. And this difference is just sigma sub k plus 1. It's the next singular value. Okay, so this is what I've been saying for the last few minutes. The way to measure how good an approximation is you need a measure of distance or a measure of length. And then you just say, I want the thing that has the closest distance to the thing I want to approximate. That's exactly what this theorem is saying. If you take any rank k matrix at all, the one that's closest in distance to A is this A sub k, and that's why we call it the rank k approximation. It's really just a rank k approximation, but it's the best one. Okay. Now, this theorem, in terms of proving it, we're not going to prove it. So, no proof given. But we can prove this. This part we can prove. Quite easily, actually. Right? The point is just the following thing. So if you look at this matrix A minus AK, I want to show that this thing has norm sigma sub k plus 1, right? Well, what is this thing? A is the full sum of R matrices, and the rank k approximation is just the first k of them, which means that the difference is all of the ones from k plus 1 to R. Right? And by the same thing that we discussed last time about why you could break up the singular value decomposition into R different pieces, this ends up being just, if I take all of the trailing singular vectors here and all of the trailing singular values here and all of the trailing singular vectors here, it ends up being the same thing as the sum. Okay. We proved an equality, or we at least explained an equality like this last time. Okay, but this is the singular value decomposition of A minus AK, because it satisfies all the properties of a singular value decomposition. It's the reduced SVD, I guess. Right? These singular values satisfy all the correct properties. The U's are still an orthonormal set of vectors. The V's are still an orthonormal set of vectors. So this satisfies all the same properties. So this is an SVD. And we show that the SVD tells you the 2 norm of the matrix. It's just the largest singular value. So this means that the 2 norm of this difference is just sigma sub k plus 1. Okay, so what this is telling you is that if you the singular values tell you how good your approximation is. If you have large singular values, then you want to include them in your approximation, because as the singular values get smaller and smaller, they matter less and less in terms of how well you can approximate the matrix. That's to say, most of the information about the matrix is contained in the first largest singular values. And you can kind of understand this geometrically, because what these rank k approximations are doing are they're not doing the full matrix A, which means that they're not doing this full picture, but they're kind of doing the bottom part of the picture. In other words, the rank 1 approximation only cares about the first singular value and the first singular vectors. So what it's doing is it's mapping this sphere to this degenerate hyperellipse. But of course, if I'm trying to approximate this 3-dimensional hyperellipse with a 1-dimensional hyperellipse, the best I can do is I should choose the largest axis of the ellipse, right? The most salient feature of the ellipse is the length of these semi-axes, right? And the best approximation to the ellipse is to take the largest one and call that, okay, well, this is, if I'm only allowed to have a 1-dimensional hyperellipse, which is just 2 points, then I might as well choose the 2 points that are the longest semi-axis. Okay, well, if I'm only allowed to have a 2-dimensional hyperellipse, what's the best choice? I should choose the 2 bigger axes of the hyperellipse, and I should choose that ellipse, and this is the closest 2-dimensional ellipse to the 3-dimensional hyperellipse. Right, and if I'm allowed to have a full 3 dimensions, then I should take the whole hyperellipse. So really, this picture also shows what's happening in these rank k approximations. Since you're choosing the largest dimension, since you're choosing the largest singular values, first, you're building up the hyperellipse, right? Of course, A is the full linear transformation, right? So here, I'm reusing this diagram. Call the first one A1, that's the rank 1 approximation, A2 the rank 2 approximation, and A is the full thing. What it's doing is it's building it up one at a time, starting with the largest axes, and then going to the second largest axis and the third largest axis, and it's building up the hyperellipse this way. So you can sort of visually see that you're getting you should start with the largest one because it's closer to what the ellipse is than if you started with just sort of any one or a smaller one, right? So let me erase this because at this point in the notes, it's just representing what would happen if the matrix A actually had a different rank. Okay, so hopefully today's lecture, along with the other lectures, gives you some idea of what information the singular value decomposition is capturing about the linear transformation. I mean, the singular value decomposition is capturing all of the information, right? It's equal to A. But how you can interpret the different pieces that are coming in this factorization as a U sigma V transpose, right? This picture and this picture are really telling you what is the singular value decomposition doing. And you should keep this in mind as we study applications of the singular value decomposition, because I think in some classes, right, I don't actually know because I haven't read any syllabi or anything, but you learn principal component analysis, you learn it, you just learn mechanically how to do it. That doesn't really mean that you understand what's happening. But now if you can internalize what the singular value decomposition means, principal component analysis is actually just singular value decomposition, where the principal components end up being, spoiler alert, will end up being these axes. The first principal component is the longest axis, the second principal component is the second longest axis, etc. And so if you have this picture in mind, you can have a better intuition for how these applications are actually working. Okay, but I see we have about 10 minutes left of this lecture. So what I want to do is I want to give you a nice visual representation of what a good low-rank approximation to a matrix actually means. Okay, so this is something that I presented to my 308 students. So if you added me for 308, you've seen it before. That's why it's written in Mathematica as opposed to being written in Julia. But it's just implementing a singular value decomposition and then looking at the output. So you can almost certainly implement this in Julia, I think. In fact, if you would like to do that and send me your Julia file, I'd really appreciate it. Then I would have it in Julia. Okay, so what are we going to do? We're going to take an image and we're going to look at a low rank approximation to the image using singular value decomposition. Well, how do you think of an image as a matrix? It's very simple. Okay, so let's say you have a 800 by 1200 image, right? So 800 rows of pixels and 1200 rows of pixels. What you could do is you could just form an 800 by 1200 matrix, and for each entry of your matrix, it will represent one pixel. Of course, usually, or one way anyway, to represent an image is to say what the R, G, and B values are at every pixel. So really, when I say we're going to store it as a 800 by 1200 matrix, I really mean we could take any image and store it as 3 800 by 1200 matrices. The red color data, the green color data, and the blue color data. Now, what do you expect for those matrices? If it's like just a regular old image, you would expect not that many linear dependencies between the columns. The columns will kind of be pointing in random directions if you're just capturing the red value at every point. Right? Of course, if you had like, I don't know, an image that was entirely white, right? Then every column of your matrix would just be 255, 255, 255, 255, and so you'd have a rank 1 matrix, right? If you had it was half white and half black, then you would have a rank 2 matrix, right? You'd have like 255, 255, 255, and I guess black would be 0, 0, 0. If you had like half white and half dark gray, you'd have like a... No, that would still be rank 1. Because they would be they would be multiples of one another. If you had like a checkerboard pattern of black and white, then you might have a lower rank matrix because there's a lot of dependencies amongst the columns. But if you just take a picture, you would expect basically a full rank matrix. If it's an 800 by 1200 image, you expect a rank 800 matrix. What can you do with SVD is you can approximate that matrix with a low rank matrix. So maybe I want a rank 100 matrix. What I can remember is just 100 left singular vectors, 100 right singular vectors, and the 100 largest singular values. That would create an approximation of the matrix that was rank 100, and you could store it by storing much less data. You only need to remember 100 vectors, and 100 values. That's actually much less than storing 800 by 1200 matrix. And because we're doing this with images, we can actually see what the approximation looks like. Okay, so here's what I'm going to do. First, I'm going to load an image into Mathematica. I chose back when I first set this up, I chose this image. I'm pretty sure I just Googled puppies, and this was one of the top hits. And here I'm going to specify the number of singular values, in other words, the rank of the approximation that I want. Okay, so let's start with a rank 100 approximation. Okay, so I've loaded in this image as image. Let's separate out the colors into the 3 color channels. Okay, so here's the red channel, the green channel, and the blue channel. You can kind of see this because, like, you know, around the bottom of this puppy's face, the fur is like pretty red. It's like reddish brown. So you can expect a lot of red to be coming through. And if you look on the red channel, it is indeed pretty light colored here, meaning that it has a high RGB value, which means it has a high R value, I guess. Meaning there's a lot of red coming through in the lighter portions of this, right? And similarly, like in the background, there's a lot of green. So you can see that the green is pretty bright. There's also a decent amount of red, I guess, in the background, like here, right? Okay, now let's take a look at how Mathematica is actually storing these channels. So what I'll do is I'll look at just the first of these channels, right? Because there's 3 here. And I want to know the height, the width, the rank of that matrix, and I want to take a look at the first few entries. Okay, so it's an 800 height and 1200 width. And the rank of the matrix is 800, which is roughly what you expect. You expect it to be a very high rank matrix. And here are the first few entries. So it's not storing them as 0 to 255. It's storing them as 0 to 1, where you have to multiply by 256, I guess, to get the RGB value. But you can see these are all pretty high because there's a lot of red in the upper left, right? It's quite light. There's also a lot of blue and a lot of green because it's just a light colored part of the image. Okay, now what we can do though is we can compute the singular value approximation using only the first 100 singular values. So that's what I've done here. So now I've figured out the first 100 left singular vectors, the first 100 singular values, and the first 100 right singular vectors. And I've created this new image out of that, new image 1 data. And this thing has rank, it should have rank 100. In fact, we should test that. I wonder if this is going to be bad. New image 1 data. Let's do that. Yeah, it has rank 100 as opposed to rank 800 before, right? So let's take a look at the original red channel. So this is the original, this is a visual depiction of the original 800 by 1200 matrix. And here is the rank 100 approximation, which is much lower than 800. But it should be the closest rank 100 matrix to this one. Let's see what that looks like. And you can see it's shockingly good, I think. It's certainly not as crisp as our original image. It can't be. I've compressed it, right? I'm not remembering. There were 800. I mean, the column space had rank 800 before. I'm only remembering 100 of the directions out of 800. But I'm remembering the 100 most important directions, the ones associated to the largest singular values. And you can see that this approximation is pretty good. And we can do the same thing for the green and the blue channel. I mean, we could always just look at the red approximation, but it's more fun to look at the full approximation. So here I've put together the rank 100 approximation using the red, green, and blue channels, and you can see it's definitely the same picture. You've lost something, but it's sort of hard. It's sort of amazing that I'm only remembering 100 singular values out of 800. Which is like 1/8 of the singular values, right? But this is definitely more than 1/8 of the information contained in this picture because I found the best rank 100 approximation to this matrix. Okay, so I'll include this. I mean, you can also just figure out how to do this in Julia. You could play around with a number of singular values, right? So let's go down to a rank 50 approximation, say. So now I need to redo the singular value decomposition here. Right, and then let's just make sure that I've gotten a worse quality image because I've lowered the number of singular values. That's true, right? So the image quality is not as good, but again, this is only 50 singular values out of 800, so that's like 1/16 of the information. But you can, I mean, it's definitely a recognizable image, right? So you do the same thing with it's always better to see it in color. And here's the rank 50 approximation. Okay, so again, it's only approximation. It's a lower rank approximation, but this is the best rank 50 approximation to this rank 800 matrix. And you can actually see that it is a good approximation, much better than if you were to choose a random approximation. I mean, I don't even know how you do it other than doing the singular value decomposition. Okay, so I think that this is pretty cool. I'll leave the notebook file on Canvas, so you can play around with it if you want. But it's just a way that you can literally see what a good low rank approximation to a matrix really means. All right, hope you enjoyed that little end of lecture bonus. See you next time.